Hi everyone. In this video we discuss a category of initialization strategies that is referred to as sparse initialization. And the basic idea of sparse initialization is basically that although you have many or a lot of weight parameters on your network, but the prior belief that we have is that the final solution will basically consist of a few of these parameters that will govern the solution. A few of these parameters will have significant non-zero values. And that's why we initialize only a few to be non-zero and the rest to be zero. And basically, if you think of it from an optimization standpoint, it's as if you have a very large parameter space, but you believe that the final solution will occupy only a small subspace out of this large parameter space. So what I mean by this is that, for example, if I have a two-dimensional space, then I believe that the final solution will look like a line. I don't know which line will it be, but I believe that it will look like a line. So this is the basic idea behind it, right? And that reminds us to reiterate over an important concept, which is the distinction between the complexity of the hypothesis space, which is basically defined by the number of parameters that you have in your network, and the complexity of the final solution that you get, right? Which is defined by how the model look like after training ends, right? So, for example, it's very common to have only few of the nonlinear activation functions being active at the end of training, right? For many of the tasks that deep learning is deployed for. So the wisdom or the intuition behind sparse initialization is similar to the fact that you end up with sparse nonlinear activations, but instead of for the units, it's for the weights. Now, if that prior belief is indeed correct, it can speed up computation time significantly because you're basically optimizing a much smaller number of weights corresponding to each hidden layer unit, right? Now, there are many challenges that appear or that are associated with sparse initialization. For example, choosing the right scale of weights, right? So in the previous video, we discussed that if you starting with initial large weights can be advantageous for speeding up the optimization process, right? But it could be a very strong prior belief. Now, this can especially cause problems if you have sparse initialization. And the problem is the following, that because you're not optimizing over many weights, right, for each connected to each unit. So, for example, if I have a hidden layer unit and these are the weights coming in, right, only few of these weights, let's say this one, and this one, right, are the non-zero ones, right? So if any of them is initialized to a so let's say I choose the initial weight value from minus 1000 to 1000, right? That means it could be anywhere from zero, the magnitude from 0 to 1000. So let's say this one here is has an initial value of 2, and this one has an initial value of 900, right? It could take a really long time to fix that 900 value if it's not correct. So if the final solution ends up that it should be a small weight value, it could take a long time because only a few weights are working to fix that bad initialization, right? On the other hand, if I'm not doing sparse initialization, then many weight values will basically work together. You can think of it like this to bring down the incorrect value. So having bad initial values could be problematic, especially if you have a hidden unit like the variant of ReLU that we discussed before, which is max out, which is choosing the maximum value, right? And the problem with max out and when we discuss convolutional networks, similarly pooling, the same thing can happen, is that basically the unit is learning only through the maximum value. So all the other parameters are not really learning, right? So when I compute the gradient and do the parameter updates, no updates are happening except to the maximum value. So it could really block the other units if you have the combination of sparse initialization in general for the whole network and max and something like max out an abundance of max out units as hidden units inside the network, and a large scale of weight, right? So so it really becomes a problem to start with large initial scale of weights when you have sparse initialization. And that's why it could be tricky how to if you are using sparse initialization, how to start, how to set the initial scales of weights. And sometimes it can be beneficial to have that initial scale as a hyperparameter. Hyperparameter meaning it's like the learning rate, and then either you do trial and error, or even that hyperparameter you could have it, you could try multiple ones and then learn automatically which one you should choose. Even the choice itself of dense versus sparse initialization, right, could be a hyperparameter. So meaning that I could switch it during training, or like by resetting training and doing, if I was doing sparse initialization, to do dense initialization. And I can having it as a hyperparameter. If I decide to make it learnable, I could even compute the gradient with respect to it, right? So, but of course, the cost of choosing something as a hyperparameter and maybe using an external method to choose that hyperparameter by trying multiple values and running multiple versions of the training algorithm in parallel, that could add computational overhead, but the advantage is that you get more flexibility. So so how do you choose, like if you make it a hyperparameter, what are some of the ways that exist that people have tried to evaluate a choice for such a hyperparameter? One thing is that you could monitor the range of values for activations and gradients over many batches. So I get few groups or many batches of training examples. I watch how the hidden units, right, the values for the hidden units and the values of the gradients. So I monitor the gradient for basically that the gradient doesn't vanish, the gradient doesn't explode, the gradient has a consistent direction. If all these things are happening, then there is no problem. If some of these are happening, then the problem could be the scales of the weights, right? Or there is, so basically that learning is not going in a good direction. The navigation of the parameter space is not happening in a way that is reactive to the cost function. So that could be a signal that the initialization is bad. Another thing is that the activations could be insensitive, right? So some of the units are not active at all. So at the start of training, typically you need to see a lot of dynamism, so that you're really exploiting the expressive power of the network. Most of the network is really learning or given a try to as many hidden units as possible to be active and learning, right? So one reasonable strategy is to start with small scales for all the layers, small scales of the weights, and then repeatedly watch for the first layer with unacceptably small activations. That means that layer, the small scales are not good for it. So you increase the weights gradually for these layers with unacceptably small activations, right? So instead of pre-assuming that you need large initial scales of weights, no, so you start with small scales of the weights and you see if learning is too slow, right? And then you increase only the scales of the initial weights for wherever it's needed, basically, right? So you could start first by watching the activations. If there are activations that are not working at all, then you pick the first layer that has such a phenomena, and then you increase the weights for that layer, and then you keep going, right? If you are done doing this and training is still slow, then you start monitoring the weights, right? So you start monitoring the first layer where the parameter updates are not changing the weights by much, and then you increase the scale of the weights for these layers, and then you resume training and so on, right? So it's basically like the current wisdom to deal with this problem of optimization with large initial scales of weights combined with sparse initialization is to start with small initial scales of weights, and then you fix these small scales of weights as you need on the go by watching the activations and by monitoring first the activations and then the weights, and then to see if training is still slow, then you increase the weights, the scales of weights for layers gradually as needed. Thank you.